Hello all, welcome to this PTX series videos where we get to try our hands-on with the Renesas NFC solutions. You may already be familiar with the PTX-105 IoT module, which is a small footprint NFC reader and host card emulator suitable for extremely portable operations. Renesas provides the SDK that can be compiled directly for ARM Cortex MCUs and also comes with an example project ready to go. In this video, we are going to compile and run that example project. This example project provides a blueprint for IoT applications showing the appropriate use of different APIs associated with the PTX module. As a primary functionality, the example project has a card reader as well as host card emulation. Developers can also choose to enable different NFC protocols, making the application compatible with various types of cards. The application contains functions to handle different NFC protocols and can be used to detect different types of cards. It also contains the API implementations specific to the NFC operations and shows example of how they need to be used with applications. As we scroll down, we will see that the definitions for different card protocols are provided as switch case statements, so allowing the use of different data processing methods for the type of detected cards. To start, we shall launch the primary development tool from Renesas, the E2 Studio, which is an Eclipse-based IDE. We shall import the example project through the SDK. Once imported successfully, the project contents will be shown in the Explorer. We can open the configuration.xml file to see the project components. The various stacks are already included and configured for communications, debugging, timers, etc. The first change is to be made with the FSP, where we need to update it to the latest version available. We can do it from the BSP tab. We shall soon notice that the default board on which this SDK is based on is the EK RA4M2, which is a Cortex M33 MCU. Now, for our demo, we have a Cortex M85 MCU board, the EK RA8D1. We can change our board type from the BSP tab. This will load the configuration for the board of our choice. You will notice there are quite some changes even on the package type. Next, we would need to delete the existing linker file. It can be found under the script folder. This file is regenerated later in the project along with the peripheral settings. So we will just proceed to deleting it now. Then we will move on to modify the peripheral settings. We will notice that several of these stacks are highlighted in red, which means when we updated the MCU, these peripheral settings got reset or did not match with the new board. What we are going to do is remove the non-essential stacks because we are not going to use them with our PTX module. Of these are the USB-related stacks, UART and I2C for PTX, and a timer. So now we are left with just 5 stacks that is sufficient to run the basic application. But we notice that the pmod and debug UART stacks are still highlighted in red. We proceed with fixing the SPI stack first. Hovering over the I button, we can see that the SCI peripheral and channels are not available with this MCU. So what can that mean? If we click on the new stacks and hover to the new menu and then connectivity, we will notice that the communication peripherals available on our RA8D1 is of the B variant, which means we need to completely replace the existing stacks. We start by adding a new SPI B variant stack. We are then going to compare the settings to match with the existing pmod stack. First thing we are going to do is find the correct pin numbers that are attached to the PMOD2 port on the EK RA8D1 board. Now, the PMOD2 port is hardwired to specific pins of the MCU. So we need to make sure those pins are correctly assigned for this new board, since the default SDK is made based on the pin configuration of the RA4M2. We open up the manual and look for the PMOD section. The communication pins are attached to port number 10 or PA, and the channel is number 2. We assign number 2 to the channel setting, then we move to the Pins tab. In the Pins tab, we will navigate to the connectivity ports. We notice that the channel 2 is not selected. So, we assign simple SPI operations. This will enable the pins for master-slave communications, clocks, etc. Let's check the MCU pins which are hardwired to the PMOD2 on the board. Okay, so all are from the port 10 pins. So we will select the pins from port 10 or A for each of these. The PTX module also needs to attach to an interrupt pin. So we can see that it's pin 508 that is available for the PMOD2 port. Now going back to the interrupt pins configuration, we can find P508 under IRQ1. So we assign the pin there. This will tell the MCU that P508 is an interrupt pin now. Next, we will need to make a small modification in the SDK files related to this interrupt pin. In the platform folder called plat, we need to change the pin assignment of the interrupt in GPIO file. Next, we need to set up the chip select pin. Remember that the chip select pin is assigned within the software, so we must not assign it in the E² Studio configuration. We see that it is pin PA05 which is available with the PMOD2. So what we will do is add this pin reference in the platform SPI file. We will also take this opportunity to change the reference to the SPI channel number as it's in the same file. Now that we have referenced the pin number for chip select in the file, we shall also make sure that this pin is set as a GPIO pin on the hardware level. So we navigate back to the pin configuration. You see, by default, it is disabled. So we will make it an output pin. Once the pins are sorted, we will now compare the different settings with the existing PMOD stack and adjust the values accordingly with the new one. We can start with the bitrate. It's also important to make sure the callback function name is referenced properly. Looks about right. We can now delete the old stack. We will rename the new stack as PMOD2 SPI, which is what the SDK refers to. Alright, that sorts out the SPI port setting. Let's move to the next peripheral, which is an EWARD port for the debug messages sent to the PC terminal. Now this port also suffers from the same issues as the SPI. It requires the B variant. So we are going to add a new stack. After initial observations, it looks like there is not a lot of changes that need to be made here. Expanding the General tab, we can see that the name and channel numbers need alignment. First, we are going to make it channel 9 since that's the port easily available for us. We can then match the set baud rate here. There does not seem to be a lot of changes on the other parameters except the name of the callback function. This is important to keep aligned since it is referenced by this name in the SDK. Next, we will see that the RX and TX pins are not yet assigned. So, we will simply navigate to the Pins tab and find the SCI9 channel. We need to enable the channel as asynchronous EWARD and make mixed pin group available. Then we will see that PF15 and PF14 pins become available to be assigned. There seems to be another little issue here with the clock. Hovering on the I button, we can see that the SCI clock needs to be enabled in the settings. Moving on to the clocks tab, we will enable the SCI CLK and SPI CLK components with PLL1P as the source. Then, by changing the deviation factor, we will set the clock speed at 60 MHz for these peripherals. Then we can remove the previous UART stack and rename the new one. Okay, that looks sorted. We can now generate the project contents. This will build the APIs with the updated configuration for the peripherals. When the project contents have been generated, we will notice a small red cross in some of the SDK files. It means the code has some incompatibility with our current project settings. When we navigate to the files, for example SPI, we will see that certain lines are producing errors. Okay, these errors are basically present because the code was written for the RA4M2, which is built on the CM33 architecture. The MCU in this demo is RA8D1, which is built on the CM85 architecture. Let's see how we can fix this. For the first one, we simply have to change the variable type, since this variable is defined in the peripheral source file. Now the next one is an API call. So if you remember, we had changed the peripheral stack and added the B variant. So we need to replace the API call with an equivalent in the new stack. We will drag the calculate bitrate API from developer's assistance. Then we are going to change the argument names. This API call has a slightly different argument list, so you need to be careful about that. For the next ones, we will simply comment out the referencing to the registers because they are not applicable to this MCU. And in line 383 and 384, we shall declare the compatible variable types. Then there's another simple API call where we open the channel. This is easy to replace. A similar one needs to be done for the channel close as well. For the next change, we will simply update the API function names for the read and write operations. Then we will open the PTX debug port file from the example folder. As the first modification, we will update the data type for baud setting variable. Then there is a baud calculate function. We will update it as well. Another function, which is the baud set, also needs to be updated. The next steps are optional as they may already be in the right setting. For example, we would want to disable this app timer source file as it is not required for basic application, but may generate errors if not configured for the new platform. Another thing that needs to be confirmed is whether the right ARM family is selected in the project build options. So, from the project properties, we need to select the family of target processor as M85 since that's the board we're using and migrating the SDK to. So that's about all the settings we need to take care of for basic SDK porting. We can now build the application. When the application has built successfully, we can then prepare to upload on the board. Make sure the PTX module is connected to the PMOD2 port and UART adapter is connected to PF14 and PF15. We will proceed with uploading then. We shall select the MCU part number as the target device. And when it has uploaded, we shall open a terminal to see the log messages. We need to select the correct baud rate and terminal settings. And there we go. The console reads out the messages as we scan a sample access card. So that was a basic walkthrough on the process of porting the PTX SDK to a new platform, but within the RA family. And that's what we have for you today. See you in the next videos.